curious tone. Take a massive elephant and a single feather, suspend them both high in the air, and simply let go. In our daily experience, the outcome is predictable. The elephant hits the ground instantly, while the feather drifts down slowly. This difference is fluid dynamics. A feather has a massive surface area relative to its weight. It hits millions of air molecules that push back up, creating drag. For heavy objects, that upward push is too small to matter. The elephant simply plows through. We aren't actually seeing how gravity works in these moments. We are watching air resistance mask the underlying rule of how things fall. In a vacuum, there is no air to push back. Without that resistance, physics states that both objects will accelerate downward at exactly 9.8 meters per second squared. This creates a contradiction when we look at Newton's law of universal gravitation. That law states that gravity exerts a much larger pulling force on massive objects than on light ones. If gravity is pulling on the heavy elephant with significantly more strength, it follows that the elephant should be pulled to the ground faster than the feather. Why does an object that is being pulled harder fall at the exact same rate as an object being pulled gently? During the 1971 Apollo 15 mission, NASA tested this on the surface of the Moon, a place with no atmosphere to interfere with the results. Astronaut David Scott held a geological hammer weighing 1.32 kilograms and a falcon feather weighing just 0.03 kilograms. He dropped them simultaneously. Because there was no air to push back on the feather, objects hit the lunar dust at the exact same time. This can be replicated on a much larger scale at the NASA Space Power Facility in Ohio, which houses the world's largest vacuum chamber. When scientists dropped a bowling ball and a cluster of feathers in that chamber, the feathers fell like stones, staying level with the ball the entire way down. The evidence is consistent. To understand why it happens, we have to look at the math behind the movement. This behavior is governed by a property called inertia. Inertia is an object's natural resistance to changing its state of motion. Think of the effort required to push a heavy truck versus a light bicycle. The truck has immense inertia. It requires a massive amount of force just to get it moving at all. The bicycle has very low inertia. A tiny amount of force can move it at the exact same speed as the truck. Gravity functions like a calibrated pusher. It applies a massive pull on the elephant, but that force is required just to overcome the elephant's high inertial resistance. It applies a tiny pull on the feather because the feather has almost no inertia to overcome. The extra gravitational force acting on a heavy object is entirely used up by that object's own resistance to moving. An object's increased mass perfectly cancels out its increased natural resistance to motion. Because of this constant relationship, the rate at which an object accelerates downward does not depend on its mass. What we see in our everyday lives, heavy things appearing to fall faster, is simply the effect of air molecules obscuring the underlying physics. Beneath the visible chaos of wind and air resistance is a mathematical balance. Gravity treats all matter the same. Whether it is a feather, an elephant, or a planet, every object is subject to the same impartial equality.